Start with this simple image. On the left hand side, you see a data frame or kind of a table that has 6 variables and a label variable. Today, we are going to talk about descriptive modeling of the data. And that topic is linked with our earlier discussion of supervised learning, where we looked at this kind of data structure. We have independent variables x1 to x6 and a dependent variable label. In this problem, we model and we train our model for either regression or classification, and then we have a good way to measure the goodness of our model. And that way is using label column, we compare the model predictions with the labels, with the ground truth, with the correct values. That difference gives us the goodness of the model. Sometimes, actually, most of the times, we don't have this label column. This kind of situation. But still, we want to learn something from our data. Today, we will talk about what we can do with a data set that doesn't have labels. We just have examples, but we don't know what are those. When we talk about descriptive modeling, there are 2 ways we can look at the structure of the data. The column ways and the rows ways. We will first do how to discover the structure in data in terms of the features or columns. And then we will talk about how to discover the structure in data in terms of rows. So comparing these 2, which method, descriptive modeling method or predictive modeling method, would be more challenging to you? If you imagine in the predictive modeling, you measure the goodness of your model with respect to the label values. In here, you won't have that luxury. So naturally, descriptive modeling is more challenging in terms of evaluation of the models. So first, let's talk about how can we discover the structure in data in terms of the features or the columns. For that, first thing that comes to our mind is a technique we call principal component analysis. So before we start, are you comfortable with moving on to this topic of descriptive modeling? We have good understanding of predictive modeling. We know what are the independent variables, dependent variables. We need to train a model that can predict dependent variable, and now we lost that information. We don't have labels now. In that situation, we still want to have some capability to understand what's going on in our data. Would you be interested in that?
Yes.
It should be more challenging, but since we get most of the data as unlabeled, so this is higher in demand modeling technique and approach. So first thing that we are going to look at is how to deal, how to discover, how to manage the relationships in the features columns of the data. And the first technique is principal component analysis. When we talk about principal component analysis or PCA, there is one keyword that we should keep in mind, and that is the core of PCA technique, and that is collinearity. Collinearity, looking at this data, can be understood as relationship among the variables, among the features. Here we have how many? X1, X2, X3, X4. You can see that X1 has a range of around -10 to +10. x2 has a range of around -5 to +12, and so on. Looking at this data, do you see any relationship among the columns? It's just a data set, right? We cannot possibly just look at these values and see in how x3 is related to x1, but there is a way to find out if x1 is related to x2, x1 is related to x3, and how much, and that is correlation. We have a statistical measure that measures how two variables are related and how much. For that, if we plot the correlation, the scatter plot of this data, we will see that x1 is related to x2 negatively. So x2 values, when they increase, x1 values decrease. x3 is also negatively related to x2. And x3 is positively related to x1. So these three plots are showing the pairwise correlations among our variables x1, x2, x3. Now, using this scatter plot, we should be intrigued to measure how much they are related, their correlation. Interestingly, I generated this data using these equations. So x1 is a simple Gaussian that is centered on 6, and the standard deviation is 8. The x2 is centered on 10, and standard deviation is 18. Then x3, I'm creating from x1 and x2, multiplying the value of x2 with 2 and adding it with x1. x4, I'm just creating it, x4 value is created using this equation. So I'm multiplying x3 with 0.45, x2 with 0.58, and x1 with 1.3. So the basic idea is that original variable is only one, x1. All other variables are just linear combinations of x1 or x2. That's why we see this kind of strong correlation among the variables. If we want to measure the correlation, numbers actually are very high. So x1 and x2, the correlation is negative 0.68. x1 and x3 is 0.81. And x1 and x4 are 0.98. If you remember, correlation is a measure that gives us the strength of relationship, positive or negative, between two variables. That value can be -1, between -1 and 1. So here we can see that x1 is strongly correlated to x2, x1 is very strongly correlated to x3, and x1 is extremely correlated with x4, 9.8. Similarly, x2 is strongly negatively correlated with x4, x2 is very strongly correlated with x3. So this correlation matrix is just a numeric form of this scatter plot. Scatter plot is showing that all variables have good relationship, and here are the equations that I used to generate this data, and these numbers are the correlation numbers. If two variables in the data set have high correlation, that situation is referred to as collinearity. We started our discussion with principal component analysis, I mentioned that there is one keyword that is at the core of PCA technique, and that is collinearity. Collinearity means when two or more variables have high correlation. That correlation has something to explain the structure and the relationships among the features, among the variables, among the columns of the data. And we can capitalize, we can use that relationship between the variables to explain. Now, when there are relationships among the columns or variables or the features of data, there are some implications. Collinearity brings in some important consequences. Number one, when two variables are related, how shall we measure their predictability? Which column is more important for our analysis? X1 or X2 or X3, if all three are related. Their importance for prediction or for understanding the structure in data will be convoluted. They are related, so we cannot say X1 is number one important, because X1 is also related to X2. So some of the importance for X1 is coming from X2. And some of the importance for X2 is coming from the X1. They are both correlated. Many of the prediction models assume that independent variables are independent. Their name is independent. They are not correlated. In regression, logistic, or linear, we assume that the variables are independent. If they are not independent, if they are correlated, then because of the collinearity, that model that we create from correlated variables will be incorrect model. So what would be the solution? To avoid these implications of collinearity in data, we decorrelate. There should be a way we decorrelate these variables. Removing the correlation among the variables is principal component analysis. Can you imagine, on the left hand side is the original data X. When we transform it using principal component analysis, the data looks like this. The same data becomes like this. So the first variable, we create a new variable from these. I will explain how are we creating. So the first variable, we will call it principal component. Principal component 1 will explain the maximum variability in data. Next principal component will explain the next best variability in data, and so on. So the last variable will be the least important in terms of explaining the variance in data. Are you interested in learning how come in the original data X4 has very high variance, around -15 to +20, very high range, very wide range, but in the transformed data PC4 becomes the least variant? You might have suspected from these equations. So X4 is actually a linear combination of X1, X2, and X3. There is nothing new in X4. We are just multiplying values of X1 and X2 and X3 with these coefficients and adding the result and creating a new variable X4. So X4 in itself is not giving us any new information. It's just a linear combination of existing variables X1, 2, and 3. So apparently, X4 is having very high variance, X3 is having very high variance, but both X3 and X4 actually are computed, or they are correlated with X1 and X2. That's why when we transform them, the actual variance in those variables is very little. So you got the gist of it. Original data, if the variables are correlated, we say there is a collinearity issue in the data. How do we resolve that? We decorrelate. After decorrelating, we get a transformed data. Transformed data has an order. First principal component or first variable in the transformed data will explain the maximum variance, and the next one will explain next, and the next, and the last variable will explain the least variance in data. And this way we will be able to decorrelate and remove collinearity problem. Just look at the correlation matrix. For the original data, we have this, if you remember, very high correlation numbers. But for the transformed data, the correlations are zero among the variables. X1 is not correlated with X2 and X3 and X4 now. Would you be interested in learning how to remove these correlations to get a data set that is straightened, that has independent axes now? The variables are really independent. Columns are having no relationship with each other, no correlation. Would it be an interesting technique to you?
Yes, Professor. This appears to be very interesting. But I have a couple of questions, sir. First is, if we go back to the equations that you have created, yeah. So here we can see that X3 and X4 are definitely correlated or dependent on the values of X1 and X2, right?
Right.
So in the graph, then how are we saying that the correlation between all the columns or all the variables has been reduced, or they have been decorrelated? Because if the graphs are prepared based on this equation, then definitely there is a relation. So that is the confusion. Yeah.
Very good question. We have this original data that is created from those equations, and we see that on the left hand side, from the graph we don't see correlations. These are just numbers, but when we calculate their correlations, we see that X1 and X2 are highly correlated. X3 and X1 are very highly correlated. Number is 0.81. And X1 and X4 are extremely correlated, 0.98. Right? Because we know the equations, we generated this data ourselves. It's synthetic data. So on purpose, I made these dependencies, relationships between the variables to show you that we are creating extremely correlated structure of the data. X2 is dependent on X1, X3 is dependent on X2, X4 is dependent on X1, X2, and X3. But the point here is to show you that we can remove these correlations. In reality, in real life, real projects, you will get this kind of data. You will not know that which processes or equations generate those data. Here we know because we are creating a scenario, but in real life, we don't know where the data is coming from. Which processes are generating X1, which process is generating X3, are they related? We don't know. So we can use a technique to remove, if there are any correlations, we can remove them.
Okay, good enough. So my next question is, Professor, normally if we talk about predictive modeling, when we have that label structure, we have the variables and we have the dependent variable as well. So in that scenario, it becomes easier to design a model which can predict the dependent variables. So in a way, to, we want all the variables to have a relationship between each other so that it becomes easier to generate the output. Over here, we are kind of uh, decorrelating them and then trying to predict the outcome. Am I understanding it correctly?
I don't know, where did you get this assumption that if there are relationships, they will be good for prediction? Actually, it's anti to that. If
Oh,
there are relationships, relationships will confuse the model. That's what I said. The implications of collinearity is that each feature, each column, each variable should be independent. If it is not, then how important one feature is to the model calculates that importance, and based on that it predicts. We learn to predict. So if two things are correlated, model will be confused. Which one to pay attention to, x1 or x2?
okay.
So x1
Makes
and
sense.
x2 are having relationship. They are correlated. So model will have a biased calculation based, because model is unaware of that relationship. It will just look at the numbers, and the output of the model we will see in terms of linear regression or logistic regression. We will learn these numbers are then incorrect. If there is a relationship, model will learn something wrong. We want to remove those relationships. The independent variables are called independent because we assume there is no relationship. If there
Okay,
is, we should remove that. So
understood.
one of the key techniques is principal component analysis, and I'm just motivating you about the need of having this technique. How do we do that? That should be based on this matrix. So principal component analysis technique uses this matrix and uses these numbers, correlations, and try to remove them. So if we plot before transforming, these are the correlations, these are the scatter plots among the variables. After transforming, the variables are independent. There is no visible correlation, right? We want this situation for descriptive modeling. And what does PCA provide us? How PCA decorrelates? It calculates a matrix. We call that matrix eigenvectors. So for each new variable, we call them PC1, PC2, PC3, PC4 here. We have a whole matrix of 4 vectors. We have 4 vectors here. These numbers are calculated based on, I will explain how these numbers are calculated, but these are loadings, or these are the coefficients of each eigenvector. We multiply original value with this coefficient, x2's original value with this one, x3 with this one, x4 with this one, and add them up. When we add these values, see, equation number 1 is calculating the transformed variable PC1, PC2, PC3, PC4. This is how we are transforming original variables into principal components. The transformed values, original values will be multiplied with these coefficients of the eigenvector. This is an eigenvector. This is a next eigenvector. This is third eigenvector. This is fourth eigenvector. Eigenvector are the characteristic equations that characterize our data. And when we multiply the original values with these coefficients of the eigenvectors and add the result, we get a value that is independent now. No correlation. We are multiplying eigenvectors with the raw data and getting transformed data. So this becomes this via this multiplication. Okay, now let's look at how we get these coefficients. There is a core simple calculus equation where we have, this is the correlation matrix or covariance matrix A, and V vector is the eigenvector. If we multiply the covariance matrix with the eigenvector, then there is a vector lambda that we call eigenvalues or singular values. Their result with the eigenvalues vector multiplied by the V eigenvectors will be equal to the left hand side. This is a strange possibility in calculus, that matrix multiplied by vector will be equal to vector multiplied by vector. But that possibility is singular. There is only one possible solution, and through calculus we call this matrix decomposition method. We decompose this matrix into two components, eigenvalues and eigenvectors. Since we are looking at only the application of PCA, how do we derive this is not going to be the topic for now, but if you are interested, I can share the details with you later. So these two things, eigenvalues and eigenvectors, are the key that are coming out of principal component analysis. Eigenvectors are transforming our original data. Eigenvalues are representing how much the eigenvectors are going to be scaled. Right? So eigenvalues and eigenvectors are both the output of PCA. And again, A is our covariance matrix or the correlation matrix that we are using here. V eigenvector, also referred to as component loadings. Interesting thing about eigenvectors is that they are orthogonal. By orthogonality, we mean that if we have this example data set, if I ask you to find out the maximum variance direction in this data set, you will immediately say that this direction is the maximum variance. And then if I ask you what is the next maximum variance, you will say that this direction is the next maximum. And just look at it. The angle between these two directions is 90 degrees. They are perpendicular to each other, right? So these are the eigenvectors of this data. So eigenvectors are orthogonal or perpendicular to each other, and the first explains the best variance, the next explains the next best, and the last eigenvector will explain the least variance in data. Eigenvectors provide us a way to decorrelate our data. We multiply eigenvector with the original data, we get transformed data, and that transformed data we have as many variables as many we have in original data. In the transformed data, we call them principal components. Notice each component is computed using all values of the input variables. x1, x2, x3, x4 are multiplied by the corresponding coefficients of the eigenvector, and we get a new value. That value is transformed value now. Principal component 1, 2, 3, 4, and finally the lambda or singular values are the scaling factor that we don't use in getting the transformed data, but they are output as part of the principal component analysis, and they let us know how much the eigenvector is scaled. So the intuition from this image is orthogonality. These vectors put your data in a new shape where every dimension, every component, every variable is perpendicular to the other variable. And that's why their correlation is 0. When two vectors are perpendicular to each other, their correlation is 0. And this is how we decorrelate our data, by finding the maximally explaining direction or dimension of the data. That is our PC1. And the next best is PC2. And if it is three-dimensional data, we will have a third dimension. And every dimension will be perpendicular to the others. Every dimension will be independent or zero correlated to the others. So first, through PCA, we get to decorrelate our variables. Second, since first variable will be the maximally explaining, the next will be the next best, last will be the least explanatory variable in terms of variance, we can use PCA to reduce the number of variables we need to use in our applications. Looking at this data, if I label, before I was not providing you the labels, let's say we have labels blue and green. Left hand side and right hand side, if I give you two data sets, now you know they are actually one data set. Right hand side is transformed version of left hand side, but assuming that you don't know that they are same, which data set will you use, will you prefer to use to discriminate between true and false class? In the left hand side, you will need to use all variables, or maybe you can prefer to use maybe x2 or x3, but you will have to look at the data set, right, and do some judgment. But on the right hand side, if I give you this data set, you will for sure not use PC3. You will for sure not use PC4 because they are not providing much information. The variance is very low. Maybe PC1 and PC2 you will use. Am I right? Are you guys with me?
Yes.
Does it make sense? I mean, if you want to choose which data set to use to solve this classification problem, which one will you prefer to use? So the right hand
according
side,
to what you just said, you will use the first one, right? Because you have more information in the first one. You have x1, x2, x3, and x4. You can use all of those. Whereas in the second one, you can just use PC1 and PC2.
well, I would prefer to use right hand side because the variables 3 and 4 are unnecessary. They are not giving much information. We don't see that on the left hand side. On the left hand side, we have correlations among the variables. That's why we may choose to use third and fourth variable. But when we decorrelate them, we see that they are unnecessary. They are not giving much information on their own. Their information is coming from other variables. So we save 50% of variables. Let's say we don't have 4, we have 4,000 features, and half of them are providing less information or very little variance, explaining very little variance in data. So we make our model based on half of the variables. So our model will be more parsimonious, more succinct. It will take less time to train, less time to deploy, less time to manage and update, and all the benefits that you get. The less number of variables are always better. In lecture 1, we learned a concept of Occam's razor. If you can explain a fact with fewer words, fewer concepts, fewer variables, it is always better than more variables, more words, more features. So we always try to reduce number of features to follow the Occam razor's principle in predictive analytics. So principal component analysis generated features are going to be a better choice because we save on number of dimensions 50% in this example. How do we choose? So there is a technique. We on y-axis keep the proportion of variance explained by each component. On x-axis we put the component itself, and this plot is called the Scree plot. We find the elbow point somewhere here, and on the right hand side of the elbow point, these variables are explaining very little variance in data, so we can discard them. And on the left hand side, these new principal components are explaining more than 95% of variance in data, so we use them in our analysis. So this is how we learned how to identify collinearity problem in data. The solution is decollinearity. PCA gave us that decollinearity capability. It decomposes the covariance matrix into two components, eigenvalues and vectors. Eigenvectors we use to transform our original data into principal components data. Eigenvalues we can also use to choose which components we want to use. If the data is normalized, a general principle is that if we use all the eigenvectors that have corresponding eigenvalues larger than 1, then we use those. So this particular eigenvalue corresponds to PC4. So the value is 0.83, which is less than 1. So according to this rule of thumb, if we discard this principal component, we are still having enough information with 3 variables. So there are 2 ways to choose principal components: Scree plot way, eigenvalues way.
Professor,
Go ahead.
Sorry. Could you please give us some real life example of this so that we can associate it in a better way? Because this is a little kind of, for me particularly, I am not able to relate to it and understand it properly. It's a little mathematical. It's a little difficult for me to understand. Sorry.
No problem. So let's consider this data set as having some meaning. So we have x1 in your data set. We look at this x1 as the number of rooms. x2 is the lot size. x3 is some other property of the house, let's say backyard size. x4 is another variable, number of washrooms. So number of washrooms will be more when the lot size is bigger. Number of rooms will be more when the lot size is bigger. Number of the size of the backyard will be bigger when the lot size is bigger. So original variable is lot size. All other things depend on how big the plot is, how big the lot is. So if you have houses data and you want to predict the price of the houses based on lot size, number of rooms, and let's say number of washrooms and the size of the backyard, right? Would it be relevant problem?
Yes.
So in that case, all these three variables, backyard, number of washrooms, and your number of bedrooms, depend on the lot size, right? They have correlation.
Yes.
They are correlated. So if you create a model based on the original values, it will be incorrect model because lot size is correlated with all three variables positively. The larger the lot size, the more there will be more rooms, there will be more washrooms, there will be larger backyard, and similarly, if smaller lot size, smaller rooms, number of rooms. So you need to decorrelate that. If you use the same values, and there are the techniques that assume that variables should be independent from each other, they will create a model that is incorrect, right? And that is a very pertinent example to understand. So if we want to remove the effect of correlation between lot size and room number of rooms, how do we do that? We apply PCA to our data set. So PCA will transform our data set into a new data set that will have 4 variables, because in original data set we have 4. We will have 4 principal components, but they will be zero correlated with each other. No correlation. Based on that data, when you create a model, you get to have a more accurate coefficients of the model. Number one. Number two, even if you don't do predictive modeling, having your data decorrelated let you focus on the important thing. Most important thing in your data is lot size. So you will see that the coefficients that you get for the principal component 1 will have a great value, large value, high weight for the lot size, and other values will be smaller. Okay?
Okay.
Does it make sense?
Yes.
So not only this, all problems when there is correlation in the columns of the data, in the variables, you need to decorrelate that to understand it better. Principal component, the literal meaning is that you don't want to get confused by hundreds of variables because they are correlated. So you want to look at the main structure of the data in terms of few variables that are most explanatory. So our eigenvectors will give us most. If you want to sacrifice out of this 2 dimensions, which one will you sacrifice? You have less space or a limitation, you need to reduce your data. Instead, for every data point, you have 2 values, right? So you need to represent every data point with 1 value. Which one will you use? X or Y? Both are important. But if you transform your data in this way, so you can see that if you keep only the values that are on this axis, the new maximally variance explaining axis, PC1, then you will lose very little information. If you use this axis, you will lose a lot of information. So this is principal component 1. This is principal component 2. So in every data set, if there is a correlation, you want to decorrelate it and look at the structure with zero correlation. Looking at the structure of the data with zero correlation among the variables is an important requirement of predictive analytics. Got it?
Yep.
There are some limitations. The features should be numeric. If they are nominal, we cannot do PCA. Second, the features have Gaussian or at least uniform distribution. If they are skewed or multimodal or having a non-Gaussian distribution, non-uniform distribution, then PCA will lead us to wrong conclusions. And third, the relationships among the variables are linear. If there are non-linear relationships among the variables, some interactions, then PCA will be counterproductive and we will lose those interactions in the knowledge of the interactions. Fourth, the variance of principal component 1 is the most explained by principal component 1. Variance in data is explained by principal component 1, PC1, the most. But that doesn't mean that we are good for prediction using PC1. Maybe the other PCs are better. So explainability of variance doesn't mean predictability. So these four are the key points that you should keep in mind. And in summary, before we conclude, we revise that if there is a correlation among the variables, it's referred to as multi-collinearity problem. Given certain assumptions, we can apply PCA to remove that. PCA decorrelates variables, and the limitations are data should be numeric, variables should be distributed in a normal way or uniform way, and so on. All right? So we will